The purpose of this video is to look at differentiation from first principles, so to use all those limit ideas that we've been developing. So just a bit of revision on function notation to make sure we know how to do this. I got a cyclist going over from a start line according to this equation. F of x equals x squared, and this is a graph of what it looks like. This is f of x, this is x, where x is in seconds and f of x is the displacement. So just reviewing function notation, find the position of the bike after 2 seconds. So I could just read it off the graph and see that it's 4. Okay, but I know that this point is going to be 2 and the function value at 2. So I know this height here is the function value at 2. So I can substitute that into my formula. Okay, and I'll see that after 2 seconds, the bike is 4 meters away. And I can also do things like finding the average velocity of the bike over the first 2 seconds. So from the starting point to that point at 2 seconds. Remember, I know this point is 2 f of 2, and this point will be 0 f of 0. I want to find the slope of that line. Okay, I'll be finding the average rate of change. It'll be the rise over the run. Okay, what's this difference in height? Well, it's f of 2 minus f of 0. And what's this difference, horizontal distance? Okay, it's 2 minus 0. So I can substitute 2 into my function. F of 2 is 2 squared, f of 0 is 0 squared on 2 minus 0, so I've got 4 minus 0 on 2, average rate of change is 2 meters per second. Okay, so average velocity during the first 2 seconds is 2 meters per second. Okay, what about instantaneous velocities? So if I'm find the instantaneous velocity of the bike after 2 seconds, I'm trying to find the slope of this. It lets me draw a tangent line. Find the slope of the tangent, and the way we'll do this is by finding 2 points that are pretty close together. Okay, so ordinarily I'll probably choose 2 and f of 2, and my other point 2.01 and f of 2.01. Okay, again, find the rate of change, this time the instantaneous rate of change. So the rise, the difference in the y values, okay, divided by the difference in the x values. So I can put 2.01 squared and 2 squared. So just evaluating what these function values are, divided by 0.01. Okay, I get 4.01, and I'd recognize that the instantaneous rate of change is probably about 4 meters per second. Okay, if I got closer and closer, I'd probably approach 4, so I would do that approximation. All right, now that we have limits, we don't need to do this thing that felt pretty dodgy of just putting 2 points close together by 0.01. Okay, what we can do instead is find the derivative, okay, which is when the difference between the 2 points approaches 0. So whenever we see that word approaches, we should be thinking, okay, this is something involving limits. Okay, so I'm going to find the derivative at x equals 2. Okay, so at this point, x equals 2, using this limit idea. Okay, so instead of having 2 and then going across to 2.01, I'm going to go to 2 plus h. So I'm going to add on h instead of adding 0.01. So I'll have the function value at 2, and I'll also have the function value at 2 plus h. So I've got 2 points, 2 f of 2 and 2 plus h f of 2 plus h. Okay, and I'm going to find the instantaneous rate of change at 2, okay, which has this symbol f dash of 2. Okay, instantaneous rate of change at x equals 2. I'm going to find this exactly the same way with the same fraction. Okay, the change in vertical or change in vertical axis or the rise of 2 plus h minus f of 2 divided by 2 plus h minus 2. Okay, the difference between these two bottom points. Okay, but what I'm going to do is this gap of h, okay, the distance between those 2 points, I'm going to make that smaller and smaller. So I'm going to make the h value approach 0, okay, essentially become 0. So I could simplify this fraction a little bit on the bottom, and I note that 2 plus h minus 2 would just give me h on the bottom. And the distance between those 2 points is just h. Yeah, the run is h. So what I want to do is be able to substitute in 2 plus h and 2 into my function. Now remember my function is x squared, and try and find instantaneous rate of change at 2. So just off to the side, I'll find what f of 2 is and find what f of 2 plus h is to be able to put them into that equation. Okay, so f of 2 would just be 2 squared, which is 4. F of 2 plus h will be 2 plus h squared. Okay. Remember, if my function is x squared, whatever I put in here, I'm going to need to square. Okay, remember squaring 2 squared plus h squared? No. Okay, no. I need 2 sets of brackets to be able to expand. Okay, 4 plus 2h plus 2h plus h squared. So this is really 4 plus 4h plus h squared. Okay, so this was just off to the side. Okay, now I'm going to just substitute these two back in. Okay, so I still have the limit as h approaches 0. Okay, on the top line, f of 2 plus h, I've found that that is 4 plus 4h plus h squared. So in it goes here, 4 plus 4h plus h squared. And I need to minus f of 2, which is 4, or minus 4, all divided by h. Okay, so this went there, and this went there, okay, which relates to those 2 points. And now I can simplify this limit and see where it goes. So on the top line, the 4 and the minus 4 will cancel each other out. I'll be left with 4h plus h squared on h. Give myself some room here. And now it's like all those limit problems that we've been doing. Okay, I can't substitute in 0 because I'll be dividing by 0. So on the top line, I'll find the common factor of h. I can now cancel these factors of h as long as h isn't 0. Okay, and I'm left with the limit as h approaches 0 of 4 plus h. Okay, now I can substitute in my h value, and I'm just left with 4 plus 0, which is just 4. Okay, so by this process of differentiation, okay, and using the limit and making the 2 points really close together, I've shown that the instantaneous rate of change at 2 is exactly 4. I haven't had to do any, oh, it's 4.01 and then, oh yeah, approximately 4. Okay, didn't have to do any of that. Okay, just have the instantaneous rate of change at 4. Okay, so if someone then went and asked me to find, well, what's f dash of 6, what's f dash of 7, what's f dash of 8, okay, I could do that by repeating this process for all of these points. Okay, but it'd take a lot of time. So instead, what we're after is the ability to make the derivative function, okay, f dash of x, which will give us the instantaneous rate of change for any point on the curve. Okay, so our main goal is to find f dash of x, okay, not f dash of 2 or f dash of 3, okay, the general one, f dash of x, which will be the limit as h approaches 0. So it's essentially this, but instead of using 2's, we'll just use x's. Okay, so exactly the same idea, just using x's instead of 2's, and this will give it in completely general terms, and we'll be able to use it to find all these different derivatives. Okay, so we'll try and find the derivative function for any point on the curve. So I don't know where this point is, could be anywhere. It could be here, this point x. We're going to have another point x plus h somewhere. Okay, it won't be that far away, just so that my diagram doesn't get messy. This point is x f of x. This point is x plus h f of x plus h. And what we're going to do is this point is going to get closer and closer to the other point until it's pretty much exactly beside it, which is what our limit will do. So derivative function f dash of x we'll find by the limit as the points get pretty much closer together of f of x plus h minus f of x on h. So off to the side, I need to know what f of x plus h is. I know my function is x squared. Okay, so whatever I put in there, I need to square, which means I need to square x plus h. Okay, and I know that binomial expansion, I need to write them side by side and expand. I'll end up with x squared plus xh plus another xh plus h squared, okay, or x squared plus 2xh plus h squared. Okay, so this is my f of x plus h. So I'm going to put this into here in my differentiation calculation. This is all just off to the side so that I don't get confused in my fraction. So limit as h approaches 0 of x squared plus 2xh plus h squared minus f of x, which is x squared. Okay, that just goes in there, divided by h. Okay, now I'll look on the top line and see that I've got x squared and minus x squared, which will cancel each other out. So I'll only have 2xh plus h squared all over h. Okay, again, can't substitute in h equals 0 because it'd end up dividing by 0. So I'll factorize on the top line, common factor of h, be left with 2x plus h. and h on the bottom. I can cancel these h's so long as h doesn't actually equal 0. And I'm left with 2x plus h. So I can substitute in my h equals 0. Okay, and I'm just left with 2x. So the derivative is 2x. Okay, try and get in the habit of just having the f dash all the way down. Okay, so use the derivative function to find f dash of 2. Alright, sounds pretty easy. F dash of 2 means replace x with 2, so it's 2 times 2. Alright, so the derivative at 2 is 4. Okay, well, I could find it to find f dash of 7. Okay, 2 times 7, 14. Okay, what about for f dash of 0? 2 times 0, 0. So this is telling me that the instantaneous rate of change at 0 is 0. Is that the case? Let's have a look. At 0, instantaneous rate of change, completely flat. Looks good. Okay, so this is a really useful concept to be able to find the instantaneous rate of change at any point. Okay, they do get slightly harder, and sometimes the notation is slightly different. Okay, so remember, if it's in f of x form, my derivative is f dash of x. Okay, and it'll look like this. Okay, but sometimes the function is given as y equals. Okay, so if it's given as y equals, then my derivative would be y dash, okay, or y dash of x, okay, or this other symbol, dy dx. Okay, either one of these symbols we can use. Okay, and we'll find the derivative by, instead of having f's here, just having y's. Okay, so it'd be y of x plus h minus y of x over h. Okay, this dy dx is pretty much like change in y on change in x, but as h approaches 0, these triangles approach d's. They change into d's. Alright, so I'll have a go at this slightly more difficult example. I don't even have the graph for this one, but it doesn't matter. I can still do the problem with no issues. So find the derivative function, so find the rate of change at any point of this function y equals 2x squared plus 7x. So I'm going to use the dy dx notation just because it's new and fresh and exciting. Okay, just another way of writing the derivative. So dy dx will be the limit as h approaches 0 of y of x plus h minus y of x divided by h. Okay, so off to the side here, I'm going to find what's y of x plus h, knowing that y of x is 2x squared plus 7x. Okay, so whatever I put in here, I need to do 2 times it squared plus 7 times it. So 2 times whatever this is squared plus 7 times it. Okay, so I need to do my expansion carefully. So you've got to multiply 3 things together. I'm just going to leave the 2 for the moment. Okay, and in brackets, I'm going to write the result of this expansion. So x squared plus xh plus xh, or hx either way, plus h squared. Okay, and expand here, 7x plus 7h. Okay, and now I'm going to multiply the 2 into all of these. So I'll just probably simplify inside first. X squared plus 2hx plus h squared. So I only have 3 terms. Okay, and then give the 2 to each of these. Okay, so this is my y of x plus h. Okay, so this whole expression is what's going to go in here, and y of x is going to be 2x squared plus 7x. Okay, those two will go in there. Okay, let's do that. So limit as h approaches 0, it's going to have to be a pretty big fraction line. Okay, that's all on the side. I'll write in all these terms. I'll write in my y of x plus h. This is pretty entertaining TV. Okay, so this is just all of these terms put up there. Okay, now I need to subtract y of x. Okay, this is where a lot of people make mistakes. I want to subtract 2x squared and 7x. Okay, because I'm subtracting more than one thing, I need brackets around here. Okay, that's a big mistake that's commonly made. Okay, so in this step, all I'm going to do is expand this negative. Okay, essentially multiply those things inside there by -1. If you don't have a good setting out, you get no chance. So minus 2x squared minus 7x. I'm going to look for terms that can possibly cancel. Okay, this 2x squared has a buddy over here, minus 2x squared. This 7x has a buddy here, minus 7x. And the other ones don't look common. Okay, and I'll just write whatever ones are left over. Again, can't substitute in h because it would be divided by 0. So I'm going to need to factorize the top line. All I need is a common factor of h. Take a h out of all of these, we'll be left with 4x plus 2h plus 7. Okay, cancel, cancel, as long as h isn't 0. Okay, and I'm left with the limit as h approaches 0 of 4x plus 2h plus 7. Okay, and I can substitute h equals 0 in here, and I'll be left with 4x plus 7. Okay, so my derivative function, dy dx, is 4x plus 7. And I can use that to find the slope at any point. Okay, so if, for example, it says find slope at x equals 2, I would find, alright, dy dx, this is weird notation, at x equals 2, I'd substitute it in. 4 times 2 plus 7, 15. Okay, the slope at x equals 2 is 15. I can do that for any value, and from there can make a graph of the derivative without having to draw slope diagrams or anything. Alright, so from here, need to practice heaps of these. I'm going to put up a solution of one of each of them, so you can use it to, I guess, guide your revision, and those solutions will come up just in here, in between here and here on OneNote. Alright, we're done here.